Hello again, Mick McQuaid here on day 12 of iste780, and we have the second of our 3 labs today in this video, and I will be speeding through this as I did with the previous one, although that's not always going to be the case. So this one, basically, we're just doing ridge regression and the lasso is our lab for now. And I've already typed in all my commands. This just clears the screen. So if you recall, I think I mentioned, maybe I didn't mention, that in order to use GLMNet, so that we're using a different library now, and you're probably going to have to download that library. I think this is the one that I had to download, I was mentioning last time. To use this, we use different notation than we would use for linear LM and GLM. So this is different notation, and we how do you say it? We split the data set up. So we put the response variable in Y, and the predictors in X. So we create a matrix of predictors and a vector of responses to start with. Okay, and then we create this grid. It's just sequential. And then we create the model. Ridge.mod is our ridge regression model, created with GLMNet, giving X as the independent, Y as the dependent. And alpha equals 0, we're just going to do when we do ridge regression. We'll switch this to alpha equals 1. We'll use the same function to do the lasso, just with alpha equals 1 instead of alpha equals 0. And so we have 20 columns of coefficients and 100 rows. So the 20 columns of coefficients are the 20 coefficients from the 19 response variables from hitters, and then the intercept, the beta naught term. And then this is for 100 values of lambda. So let's take a look at lambda 50. So lambda 50's value is 11,498. And here are the coefficients in that row of the table. And some of them are pretty small. In general, ridge regression standardizes before it starts. So the coefficients in general are going to be much smaller than they are in other models. And this is one of the more extreme ones, and you can compare this -6 to the -90, I think, in least squares or something like that. Okay, so let us continue on. So let's look at another value. So here's lambda 60, and look at that. Lambda 60 is 705. Okay, so that's a much smaller value of lambda that's moving toward least squares, and giving us substantially different coefficients here. Is that right? Yeah, way different coefficients here. Okay, and then here is the L2 norm of, well, I'm sorry, did I do the L2 norm of the other one? I'm not sure now. I think I skipped over the L2 norm of the other one. So here's the L2 norm for 50, which is way lower than the L2 norm of 60. And this is, these are the coefficients for S50. So this is a prediction. So this is doing a predict using lambda equals 50. Okay, now let's split the sample into training and test sets. And we're going to set seed so that we get repeatable results, not repeatable results, but results that match the textbook. Repeatable in the sense that we can see that they match the textbook values. We never really need this set seed 1. We're doing that artificially to maintain our consistency with the textbook. Okay, so here's ridge model, ridge pred. And so here is the mean squared error for this ridge regression model. And we can get this, we can get so this is the, what is this? This is the mean squared error. I'm blanking on this now. This is what happens when I try to hurry. I should never hurry. So the test MSE, okay, so here's the test MSE with just an intercept. Which is much higher. So that's the test MSE without any of the other betas. And we could get the same result by using a large value of lambda. So if we use a large value of lambda, it's going to be equivalent, and look, we get exactly the same test MSE. And this, the textbook mentions that 1e10 is equal to 10 billion. So this is just exponential notation, 1 times 10 to the 10th. And that's, we've actually used that notation before. R accepts that notation. We've used it before. For some reason, the textbook mentions it now. It hasn't mentioned it before. Let me mention that if we're doing small numbers, the number after e will be preceded by a negative sign. So this simply tells us to move the decimal point 10 places to the left. If it's preceded by a minus sign, it means to move the decimal point that many places to the right. What did I just said the exact opposite of what it is, to move the decimal. If this is preceded by a negative sign, we move the decimal place that many places to the left for very, very small numbers. Okay, and now I've lost my... Okay, so now we're going to make it equivalent to least squares. So the question is, does this do any better of a job than least squares? And it does a substantially better job than least squares. Unfortunately, I've let that go off the screen. Let me go back up here. So, or I guess the textbook says it's not that big of a difference, but it's the difference between 101,000 and 114,000 for the MSE. So the MSE, remember, we want to minimize the mean squared error, and the mean squared error is smaller for ridge regression than it is for lambda equals 0. Lambda equals 0 is the same thing as least squares. And we get substantially different coefficients between them, and those also are off the screen. But these are the same coefficients for making, for doing the least squares model and for making the ridge regression model equivalent to least squares. And you can see how close all these values are to each other, all the coefficient values are to each other. Okay, and so now we'll use k-fold cross-validation. So choosing lambda is it's not a good idea to do what we've just been doing in terms of just playing around with different lambdas. Instead, if we use k-fold cross-validation with k equals 10, we're going to get quite a different lambda. So we're going to run GLMNet's cross-validation method. So the GLMNet function has this cross-validation method, and we can did this not work? Is that I don't think that this is it seemed to me that this was a bit curvier than this. Okay, so I don't know, somehow, hopefully that's the correct plot. It seemed to me that this went down somewhat here when I did this before. Okay, so what is the best value of lambda? The best value of lambda is, where is it? I think there's something wrong with my communication between this thing and, okay. So I was in that mode again. I did the same thing I did once before, where I got into a copy and paste mode. When I go up and down in this screen, all these things all these things are paused until I come out of that mode, and then they're all hit at once. So you can see that I've hit best lambda 3 times. The value of the best lambda is 212, and this is the actual correct plot. So that's obviously a far cry from lambda equals 4, which we were doing before. So here is the model using best lambda instead of, so we've actually saved this as a variable, 200, this is just 212. And so here are the coefficients for our prediction for using best lambda. And again, you see that the coefficients are small. The textbook makes the point with an exclamation mark that ridge regression isn't doing any variable selection. So even though many of these are small, none of them are 0. But notice that which ones are small: assists, see at bat, see walks, at bat. So those are all really small. And what we're going to find, now we're going to do the lasso, and what we're going to find is those are going to get all zeroed out. So that's a big difference with lasso. So the lasso model is the same, except I think I mentioned before that it's alpha equals 1 instead of alpha equals 0. And here's a plot of the lasso coefficient. So this is probably division W that goes extremely negative. And what one goes extremely positive, I don't remember. Looks like new league N is the most positive one. Okay, now we're going to get, again, these reproducible results by saying set seed 1. We're going to get the cross-validation errors. We're going to plot the cross-validation errors. And we're going to find out the best lambda, which is not going to be the same thing as the best lambda in ridge regression. And I don't honestly remember what it is right now. But it gives us, oh no, wait a minute, it is about the same. It's giving us a very slight improvement over ridge regression. Ridge regression gave us about 101,000. This is about 100,000. And so now we have the lasso coefficients. And notice the things that were really tiny in the ridge model are now 0. At bat was really tiny, it's now 0. See walks was really tiny, it's now 0. Home run wasn't that small, 0.13, and it's now 0. Wow, runs was pretty big, and it's 0. But all the ones that were small, so we can't just eyeball, so I guess the moral of that story is that we can't just eyeball ridge regression and figure out what lasso would do. It is making all the ones that were small. Assists is another one. And see at bat is another one, and see hits is another one. But there are many that are not that small that I would not have guessed that the lasso would zero out. So we don't now only have 7 variables. That's really the point that the textbook makes, is that we have the lasso. We have 7 non-zero predictors here. So this is in the same general area. Actually, we were a little bit better with ridge. Come to think of it, the best we did with ridge was 96,000, wasn't it? I don't know where I got that 101,000. I think that was from, that was when we just did lambda equals 4. So when we had lambda equals 212, we got 96,000. So that's the best mean squared error we get from ridge regression with however many variables we've got here. But then when we go to lasso, the lasso, we wind up with slightly worse mean squared error. Okay, not that much of a difference in the mean squared error, but we've dumped a bunch of variables, and we have, let's see, 1, 2, 3, 4, 5, 6, 7, 7 variables left. So if you recall, I mentioned the other day Occam's Razor and the notion that a parsimonious model is to be preferred if two models are similar. That was in the context of the one standard error rule, where if the most parsimonious model is less than a standard error away, which I don't know that it is here, if it's less than one standard error away, then use it. That rule, though, was in another context. But here, these are very close. These are very similar. And so, if it were up to me, I would use the lasso. I prefer the more parsimonious model. I'm distrustful of larger model. The larger the model is, the less I understand it, and the less I trust it. Okay, so thanks for your attention on this. We just have one lab to go now for today, so bear with me. We'll speed through this and then get back to the regular level of detail tomorrow. Thanks.